The universal law of gravity. Okay, so if you remember before, we've talked about the force of gravity and we've talked about acceleration. And one of the problems on your previous homework asked about the difference between the force of gravity and acceleration. Okay, so one key thing to note is that the acceleration due to gravity here on Earth is a constant. Okay, so it would be 9.8 meters per second squared. Okay, for the force of gravity, we have that the force of gravity equals the mass of the object times acceleration, where acceleration is our gravitational constant of 9.8 meters per second squared. Okay, so acceleration is going to be constant here on Earth's surface, but the force experienced from gravity is going to be different depending on the mass of the object. Okay, but this value of gravity does not always work for all different objects in space, such as the sun, different planets, and things like that. And it actually is not a constant for if you are significantly above or below the average radius of the Earth. Okay, so if you're not directly on the surface, like if you're at the peak of a mountain, or if you're like skydiving and things like that, the value of gravity, the acceleration of gravity might be slightly different. Okay, so how do we calculate this gravitational force, this attraction between the different objects, if we don't have the constant acceleration? Okay, so Newton allowed us to kind of figure this out, and what he basically said was that objects in space, and so here's my image of Earth. Okay, if we have Earth and it has a mass of 5.972 times 10 to the 24th kilograms, okay, if that's the mass of the Earth, he just stated that even these large objects can be considered as just a point, okay, with all of its mass concentrated in the center, okay, and so this would equal, same thing, a mass of 5.972 times 10 to the 24th kilograms, okay. And so using this fact, we can find the gravitational pull between two objects. Okay, and so with this, we're going to be using a different symbol to represent this. So instead of a lowercase g, which is what we use for the constant value of gravity experienced here at Earth's surface, the force of any gravitational pull between two objects is going to be proportionate to the mass of the two objects divided by the radius squared. Okay, an important thing to note is that the radius squared is just the distance between the centers of the objects. Okay, the other important thing to note is that it is in meters. Okay, so a lot of the time, especially because we're talking about objects in space for some of these problems, it's going to give it to you in kilometers, and so you're going to have to convert it to meters before you move forward with the problem. Okay, so just be aware of that. And then the mass of the objects are going to be given in kilograms. So I'll kind of just label that as well. So we have the mass of the two objects, and it is given in kilograms. Okay, so if they were to give it to you differently, you would have to convert that. Okay, But this is not equality, okay? So for the two sides, we do need to factor in the universal gravitational constant, which is given to you here. And for tests, I will give you this value. You do not have to memorize it. But like I was saying before, we're going to represent this with a capital G instead of a lowercase g. So the universal gravitational constant is given a capital G to distinguish it from the lowercase g, which is the constant of acceleration of gravity here on Earth. Okay, and there's just a little note in here too that kind of helps you remember the difference between the lowercase g and the uppercase g. The universe is bigger than here on Earth, so it gets the uppercase g. Okay, so the formula in order to calculate the acceleration due to gravity here, or the gravitational force, is going to be F of g equals our gravitational constant, our universal gravitational constant, which is that 6.67 times 10 to the negative 11th, times mass of the first object times the mass of the second object, once again divided by the radius squared. Okay, and g is going to be this value here that I highlighted. Okay, so r, once again, is just the distance between the centers of the two objects. Because remember, no matter how massive the object is, we are going to assume that it is just this point. So we're going from point to point, where the point is the center of the object, and we assume that all of the mass is there at the center of that object. For this example, I'm just going to pick two different masses of individuals that we're going to use for this problem. We're going to see how attracted the two members of our class are to each other as far as gravitationally. Okay, so the masses and distance would vary if we did this in class with everyone. If you knew your mass, we could calculate it between multiple ones and then measure the distance between your guys' desks and then find what your the gravitational force between you two. Okay, so let's just say that the mass of the first person is 65 kilograms. Okay, and then the mass of the second person is 85 kilograms, and then the distance between them, or distance between their centers, is going to be 1.5 meters. Okay, so these are just values that I made up just for the purpose of showing this example. So we want to know what is the gravitational force felt between the two objects, or the two people. Okay, so remember again, our equation for f of g is that we have our gravitational constant times the mass of 1, the mass of 2, over r squared. Okay, so plugging it in, we're going to put in the constant, so 6.67 times 10 to the negative 11th. Times our mass, so 65 kilograms, and then times our second mass of 85 kilograms, divided by the radius squared, so 1.5 squared. Okay. Now, if you have like a graphing calculator or a higher functioning calculator, you should be able to kind of put all of this information in easily, and it will compute the correct answer for you. I am going to just go over briefly how to do the how to multiply and divide scientific numbers. So in case you've forgotten from previous classes and things like that. Okay, so the first thing I'm going to do is I'm going to square the denominator, so 1.5 squared, and we're going to get 2.25. Okay, and then Just for ease, I'm going to convert the values that we have for the two masses and the radius into scientific notation just for ease and kind of to help with explaining how to multiply and divide by scientific notation. Okay, and I'll have like kind of a cheat sheet for scientific notation attached to the assignment as well that you can use and reference for future assignments. So for this, it would be 6.5. I move the decimal place one place to the left. So it would be times 10 to the 1 power. So if I were to multiply 6.5 times 10, I would get 65 again. Okay. So if you remember from science class or from math class doing scientific notation is always going to be your first number that you're going to be multiplying times base 10 is always between 1 and 10. So it has to be greater than 1 or greater or equal to 1 and then less than 10. Okay? So you can have like 6.5, 8.5, 9.2. You can't have 10. You can't have 11. You can't have 0.6. Okay? It has to be greater than or equal to 1 and less than 10. Okay? So 85 would be split into 8.5 times 10 to the 1. Okay? And then for my bottom number, this is going to be 2.25. It's already in between the 1 and 10 values, so it would be times 10 to the 0 power. Okay, I'm just putting them all into scientific notation just so it's easier to kind of go through and do, like I said, the multiplication and dividing with using scientific notation. Okay, so when multiplying in scientific notation, you're going to take the first number that's times by base 10, and you're going to take all the numbers that are multiplying together, and you're going to just multiply those together. So we're going to take 6.67 times 6.5 times 8.5. And we would get, and I'm going to do this kind of off to the side, we would get 368.52. And then times 10, and then to find our exponent that we're taking base 10 by, we're going to add, because we're multiplying these together, we're going to add the exponents. So we have negative 11 plus 1 plus 1 from the values here. So we have plus 1 plus 1. So negative 11 plus 1 plus 1 is going to give us negative 9, sorry. Okay, and then we have still our bottom of 2.25 times 10 to the 0 power. Okay, for the dividing part, when you divide, once again, you're going to take the first numbers and you're going to divide those. So 368.52 divided by 2.25, and we get 163.79. Okay, and then we're going to have the times 10, and then whenever you're multiplying, whenever you are dividing in scientific notation, you're going to subtract the 2, okay? So you're going to take the top number minus the denominator. So negative 9 minus 0, we're still going to have negative 9, okay? So that is a correct answer. So that would be in newtons. Okay, but to be more correct and to be in scientific notation, it's not in proper scientific notation right now because the first number is bigger than 10, okay, and it has to be between 1 and 10, basically. Okay, so if I move my decimal place over, I'm moving it 2 spots, so I'm going to add 2 to my base 10 number. So my new number is going to be 1.64. I'm going to round 1.64 times 10 to the negative 7th newtons. Okay. Like I said, I will have some cheat sheets for you on scientific notation if you need a refresher on that, but I don't want to spend too much time just going over scientific notation. Okay. For the next one, we're going to use this equation, the f of g equals g m1 m2 over r squared, in order to find the force of gravity between both Earth and Sun. So here they've given us the mass of the Earth, okay? They've given us the mass of the Sun, and then they've also given us the distance between the two of them. What's nice too is they have put it in meters, so we don't have to worry about converting it whenever we're going to go plug it into the equation. So for the equation to find the gravitational force between the two objects, we take the universal constant, gravitational constant, so 6.67 times 10 to the negative 11th times the mass of Earth, so 5.972 times 10 to the 24th, times our mass of the Sun, 1.989 times 10 to the 30th, okay, divided by the radius squared. So 1.496 times 10 to the 11th, and that is squared. Okay, once again, when multiplying scientific notation, I'm going to multiply the first numbers together. So 6.67 times 5.972 times 1.989. Okay, then I'll take that times 10. And then I'm going to add the exponents for all of the values. So negative 11 plus 24 plus 30. When I do that, I get that my answer is, for the top, is 79.228 times 10 to the 43rd. Okay, now for the bottom, we're actually raising an exponent to the second power. And so when doing this, you're going to square first the first number, so 1.496 squared, and we'll get 2.238. And then for the exponent on the base 10, you're going to multiply the numbers together. So 11 times 2, you'll get 22. Okay, once again, when dividing, you're going to divide the first numbers. So when I divide 79.228 divided by 2.238, I get 35.401 times 10. And then to find the exponent that we're raising 10 by, you're going to subtract the denominator from the numerator. So the top minus the bottom, so 43 minus 22. And we would get it's raised to the 21st. Okay. Now this isn't in correct scientific notation, so I do need to move my decimal one place so that I have 3.5401 instead of 35, which is greater than 10. And so it's going to end up being 3.54, and I generally just round the two decimal places. In actuality, we should be doing significant figures, but just due to us not being in person and not wanting to spend extra time on doing significant figures, that's why I've kind of like skipped through it. And that's why too, whenever I'm looking at your work, you might have slightly different answers than I do, which is fine. That's why I'm looking at your work and seeing that you're actually setting up the equations properly, okay? So like this part up here is more important to me than your answer down here, okay? So I'm looking to see, did you plug in everything in the correct place? Did you set it up that you have it squared and all of that? Because that's the important part. I'm not so concerned with your calculator work, okay? So this would be 3.54 times 10 to the 22nd, because I moved one place to the left. For your guys' practice problems, I do just want to touch on a few of them, just because some of them are a little bit different than the practice problems that we were doing before. So for question number 1, it's going to be very much just like our practice work that we did before. The key things, though, is that you do have a mass given in grams, so you would need to convert that to kilograms, and you do have the distance apart to be in centimeters, so you need to convert that to meters before you plug it into the gravitational constant formula to find the force felt between the two objects. Okay. For question number 2, here it does give you an orbital radius. Okay. And so it's basically saying that Triton is orbiting Neptune, and so the radius of its orbit would be the distance between the two bodies. Okay, but do notice that it gives you the radius in kilometers, so you will need to convert that into meters before you plug it into the equation. Okay, and then other than that, it's pretty straightforward. You don't have to convert anything else, and you are just using the main formula that we practiced in the practice problems. For question number 3, find the weight of a 65 kilogram person for part A when they are on the surface of Earth, but use it in 2 different ways. So what that means is it wants you to find the weight, which is the force felt by gravity, using F equals ma, or m times the gravitational constant, 9.8. And then also using our new formula of F of g is constant of gravity times mass of 1 times mass of 2 over radius squared. Okay, so for part A, it just wants you to solve the equation of a 65 kilogram person with the 2 different things. An important thing to note is for the second equation, the mass of Earth and the distance between the person and Earth is given here for you guys to use in that second equation. Okay. For part B, when they are 36,576 meters above Earth's surface, okay, so you would just take the RE that's given here. Okay, so you're taking the 6,371 kilometers, and be careful of this. You will need to convert this before you plug it into this. You will take the 6,371 kilometers, and you're going to add this number to it before you plug it back into the problem. Same thing for C. Except you need to convert this to meters before you add it to the number and plug it into the equation. Okay. For question 4, it's asking find the acceleration due to gravity on the surface of Triton. Okay, so in the previous question, you should see that the force of little g is equal to the force of big G, okay? And so because of this, we can set them equal to each other. So if F of little g is m times acceleration, right? Mass times acceleration, ma. And then we know that F of g is the gravitational constant times mass of 1, mass of 2 divided by r squared. Okay, we can set those equal to each other. So the mass of the object times acceleration, so times the acceleration equals the gravitational constant times the mass of the object again times the mass of Triton in this case, so the mass of Triton, divided by the radius squared. Okay, once again, be careful. They did give you the radius in kilometers, so you will need to convert that to meters. Okay, so with this equation, you might be like, okay, well, we have the mass of Triton, we have the radius of Triton, but we don't have a mass of an object, so how can we solve for A? So if we were to get the mass of the object both on the same side, okay, using algebra rules, okay, to cancel out this and put it over here with this one, we would have to divide both sides by mass of object. Okay, and then so if we divide this side as well by mass of the object, what happens is that they cancel out. Okay, so that we're left with the equation A equals the gravitational constant of the mass of Triton divided by the radius of Triton squared. Okay, so that's the equation you're going to plug into to find the acceleration due to gravity on Triton's surface. Okay, and that would be to any of the objects dropped on Triton. For question number 5, find the gravitational field strength of Neptune. Okay, you're going to be doing the exact same thing that you did for question number 4 using the same equation, this A equals GMT, or it would be MN divided by R squared. Okay, once again, the only big thing is you need to make sure that you convert your kilometers into meters before you plug it into the equation. Okay. Lastly, number 6, question 6, you do not have to do, so you can skip that one for your homework.